In this video, we will discuss regarding the use of catalyst in chemical reaction and the mechanism of action. History of catalyst. First, we'll try to understand the word catalyst. See, the catalyst is derived from a Greek word "kataline," which means to dissolve, to unite, or to pick up. The first chemical reaction using a catalyst was done by Kirchhoff, and the term catalyst and catalysis was given by Berzelius. What is a catalyst? See, a catalyst is a substance which alters the speed of a chemical reaction without itself undergoing any chemical change. So it will not undergo any chemical change, but the speed of the reaction, it will alter the rate of the reaction. Okay, that is called as a catalyst. Now, how does it does? See, the general function of the catalyst is to provide an additional, or we can say an alternative mechanism by which the reactants are converted to products. We must also understand that even without this catalyst, the reaction can occur. So the catalyst is not initiated. Okay. For example, in the decomposition of potassium chloride, manganese dioxide acts as a catalyst. Even without manganese dioxide, the reaction can occur. But here it is acting as a catalyst, so the reaction rate is going to be fast. General characteristics. So the catalyst which we are going to use in a particular reaction, its mass and will not be changing. And very small quantity of catalyst is enough for the reaction to occur. And as we said, it is not going to initiate a reaction. It is not going to alter the position of equilibrium. So equilibrium is not going to change here. And the catalyst is generally specific in its action. So free energy of the reaction, delta G naught of the reaction, which is being catalyzed by using catalyst, remains unchanged. It will not change. Equilibrium constant, it will not change. The only thing that is going to change is the free energy of activation, it will decrease. And due to which the rate constant or the rate of the reaction will increase. So the type of catalytic reaction, general homogeneous catalysis and heterogeneous catalysis. Homogeneous catalysis, we know that the reactant and the catalyst, they are going to be in the same phase. So in the example, ester hydrolysis, here we can see the ester, the water, and the catalyst HCl is all are in the same phase. So it is called as a homogeneous catalysis. In case of heterogeneous catalysis, the catalytic process, the reactant and the catalyst are going to be in different phases. For example, in Haber's process, the production of ammonia, we can see that 2 nitrogen and 3 molecules of hydrogen are going to combine together to form 2 molecules of ammonia. The reactants are in gaseous phase, but the catalyst in a solid state. So it is called as heterogeneous catalysis. And since the reactions are going to occur on the surface of the catalyst, we call it as a contact catalysis. Heterogeneous catalysis is also called as a contact catalysis. So type of catalyst. See, there are 2 types: positive catalyst and negative catalyst. Positive catalyst, it will enhance the speed of the reaction. It's called as a positive catalyst. Negative catalyst, it is going to retard the reaction rate, going to decrease the reaction rate. It is called as a negative catalyst, which we also call as inhibitors. For example, decomposition of hydrogen peroxide. To enhance the rate, use a platinum catalyst. To decrease the rate, we use a glycerine as a catalyst. Same reaction. We're going to change the catalyst. One acts as a positive, another acts as a negative catalyst. There are also other types, auto catalysts there, induced catalysis is there. Okay, and these catalysts and positive and negative catalysts should not be confused with promoters and poisons. See, promoters, it is not a catalyst. It is going to help the catalyst. Okay. And similarly, poison, it is going to decrease the activity of the catalyst. That is what their work is. Now, regarding the theory, regarding the mechanism, see, generally when a chemical reaction occurs, the 2 reactants will combine together. They have to go to the activated complex. Okay, to go to that activated complex, it has to spend some energy. That energy is called as activation energy. Okay, this particular activation energy, once it reaches the top, okay, then it will give its product. Now, when we are going to add a catalyst, what it does is, it is going to decrease the activation energy down. So the activation energy is going to decrease. Because the activation is going to decrease, the reaction rate is going to, because more energy is not required, just some energy is enough to give the product. So that is what we are telling here. The energy required for the reactants to reach the activated complex is called the activation energy. The catalyst it is adsorbs the reactants, activates them by weakening the reactant bonds, and allowing them to react to form the product. We'll take an example of a decomposition of hydrogen peroxide. Without a catalyst at room temperature, it is 76 kilojoule per mole, the activation energy value. If you're going to add a little iodide ion to it, the activation energy falls to 57 kilojoule per mole. Then the rate constant, not the activation, the rate constant increases by a factor of 2000. Okay, so because we know K is equal to EAE to the power minus EA by RT from the Arrhenius equation. There are two theories. Since we have seen homogeneous catalysis, we will be discussing the intermediate compound formation theory, which was proposed by Clement and Desmoses. Here, the reactant A and B in presence of catalyst gives AB. The mechanism is very simple. Any one of the reactant A or B will react with the catalyst C to form intermediate compound AC. This intermediate compound will react with another reactant B, and it will give the product, and the catalyst is obtained. So it's a general mechanism. We'll take an actual example. In the lead chamber process, in the oxidation of sulfur dioxide to sulfur trioxide, nitric oxide is acting as a catalyst. It is going to react with oxygen and is going to form nitrogen dioxide. This is the intermediate compound. This nitrogen dioxide is going to react with sulfur dioxide, and we are going to get sulfur trioxide, and the nitric oxide catalyst is regenerated back. So this is regarding homogeneous catalysis. To explain this homogeneous catalysis, we have this intermediate compound formation theory. It has got some limitation. One, it is not able to explain the catalytic Poisson and promoters. And second, it is not able to explain the mechanism of heterogeneous catalysis reaction. To explain heterogeneous catalysis reaction, we require adsorption theory. So this theory was explained by Langmuir on the basis of adsorption. The reactant molecules A and B, or only A, these reactants are going to get adsorbed on the catalyst surfaces, and that's why the name is also called as contact catalysis for heterogeneous catalysis. The reactants are adsorbed on the catalyst surface to form an activated complex, and they subsequently decompose to give the product. So the first step, reactant molecules in the bulk has to diffuse to the catalyst surface. Once they come near to the catalyst surface, they get adsorbed on the surface catalyst. Once they get adsorbed on the surface of the catalyst, they are going to get activated, and they're going to form an activated complex. Okay, this activated complex is going to decompose into the product. Now the product is still on the catalyst. It has to be desorbed. It has to move. So it moves away from the catalyst, and it has to give other way for other molecules also, other reactants also. So this particular product goes away, diffuses away from the surface of the catalyst. This is what adsorption theory explains. This catalyst has a very important role to play in sustainable chemistry or green chemistry. We know that there are some principles of green chemistry. Two principles are there. There are three principles. First thing, it is better to prevent waste than to treat or clean up waste. Instead of producing the waste, avoid producing waste. So that is the first thing. Second, energy requirement should be minimized. Third, synthetic methods should be conducted at normal ambient temperature and pressure. Now, when we are using this catalyst, the activation energy is getting reduced. We are using stoichiometric reagents. The byproducts, since the catalysts are highly selective, byproducts are less, and there is no waste. So this particular catalyst helps in green chemistry and in sustainable chemistry. So application of catalyst, there are many applications. We are just giving a very few examples. In Haber's process, the manufacture of ammonia, iron is acting as a catalyst. In Ostwald process, where we manufacture nitric acid, platinized asbestos is used as a catalyst. Lead chamber process for manufacture sulfuric acid, nitric oxide, Contact process for the manufacture of sulfuric acid, we use vanadium pentoxide or asbestos. Decons process for the manufacture of chlorine, we use cupric chloride. Boost process for manufacture of hydrogen, we use ferric oxide. Hydrogenation of vegetable oils with hydrogen ghee, vanaspati ghee. There we use finely divided nickel. And Bergius process for the synthesis of petrol from coal, we use ferric oxide. So these are the application of catalysts, and the industries, the synthesis of many chemicals, okay, in oil industries, in automobile, all important industries, and in synthesizing chemicals, catalyst is being used. Thank you.